Hi, my name is Andy Boyle, and welcome to The Primer. This is a video how-to series on the Forensic Technology product line and some tips and tricks on how I think you can best use them to get the most efficient use out of them.
All right, so let's get into the fired bullets now. So to understand the markings that are on a fired bullet, we just got to go back a little bit first and talk about the manufacturing process. So for a conventionally rifled barrel, the first step you're going to do is take that rod and drill through it and make it a tube essentially. So the drill doesn't quite look like this, but the first step is really to drill through the rod and make it a tube. And then the reaming is going to happen, which a precision tool goes through, makes it a very precise diameter, very straight as it goes along as well. And those reaming marks, whatever marks are on the edge of these blades of the reamer, they are transferring a pattern during this process to that surface. Once that reaming is done and you've got the beginnings of a barrel here, the caliber it's ultimately going to fire would not fit down the barrel. The bore diameter at this stage is actually smaller than the diameter of the cartridge it's going to ultimately fire, the bullet's going to fire. The next step would be to put the rifling into the barrel. And for conventionally rifled barrels, there's two different methods. There's cut rifling and button rifling. So for cut rifling, a gang broach, which is a rod with a series of blades on it, is going to be forced down the barrel, and those blades are going to shave off a little bit of metal to cut grooves into that barrel. So here's your barrel, here's your gang broach with blades, and each one of these blade clusters here is going to look like this from the front. So you could have 4, 5, 6. The number count of how many there are could change, but each one of these, as it goes along, each cluster has got a series of blades here, and in sequence, each one is microscopically larger than the one that just went ahead of it. So this guy here is going to come in and it's only responsible to shave a little bit of metal off. The next one does a bit more and a bit more and a bit more until the last one in the sequence, it actually has the diameter here across equal to the caliber that it will be firing ultimately. So this last guy going through is shaving through that groove, and that's when it's going to be ready for the caliber it's ultimately going to fire. Button rifling is kind of similar but different in its own way. There's a carbide button, which is stronger metal than the metal of the barrel, and as that's forced down that barrel, it is going to compress those grooves in there. It's pushing the metal back rather than cutting the metal back. And so you could have 4, 5, 6. Some of these could even get into some real micro groove where you're up in a dozen of them, or even in the 20s or so. But typically in this scenario here, we've got 6 actual areas that are going to, as they get forced down the barrel, they're going to compress those grooves down the barrel. And the important thing to note here is that as each of these tools is being forced down, there is a gradual rate of twist that is being introduced at the same time. They are twisting down the barrel as they go, and they are going to go either right-hand twist or left-hand twist. It's up to the factory to decide, but they are introducing these grooves with a rate of twist as they go down that barrel. Once that's been transferred over, you've got your rifling, which are the helical grooves in the bore of the firearm that are there to impart rotary motion onto the projectile. So what happens is that rifled barrel, inside of it, you're going to have your land impression, which was not touched by the gang broach or the button, and you're going to have the grooves, which were. So this is either cut away from cut rifling or compressed away by button rifling. And each one of these areas, when that bullet goes in, the diameter across groove to groove is equal to the diameter of the caliber. It's an airtight fit. But where these lands are still present, that is still too tight. These lands are going to grip into the side of the bullet. And because there is a helical pattern to these, because there's a rate of twist there, as that's gripping into the bullet and the bullet's going down the barrel, that bullet has no choice but to start to turn with those with that rate of twist, and it's going to continue to spin as it exits the muzzle of the barrel. And it's that spinning motion that the bullet has that's going to keep it stable as it flies through the air. That's what's so important about that rate of twist, is that it's there to keep that bullet stable as it's going through flight. And as it leaves the barrel, when you're looking at that bullet afterwards, where that land was is going to leave you with a land engraved area, or LEA as we call it, LEA, LEA. And where the grooves were is going to leave you with a groove engraved area. And that's where the markings have been transferred across, especially in this area here where it really dug in. The land engraved area is giving you the strongest marks typically. So if we take a closer look at that, here is one LEA. So just one of these areas here, we're got a close up zoom in on here. At the base, you've got the striations there, the scratched pattern that was left across the surface. And typically you get the best results of looking at that at the base of the bullet, especially when you've got a flat-based bullet like this that is jacketed material there, like copper jacketing over a lead bullet. That is going to give you, the last 2 millimeters are really the area that we are most concerned about when you're doing work on a bullet tracks machine. On either side here of the land impression or land engraved area, you've got two shoulders. And those shoulders are where you've got the height transition from the high G down to the low LEA. And so the LEA begins right at the bottom of that shoulder and continues to the bottom of this shoulder. So this area here, all the way across to this area here, with that being the shoulder itself, this lower area with the slightly darker color to it, that is your LEA. That's the area we're most interested in with IBIS. Other areas, you've got a driving shoulder and you've got a trailing shoulder for each one of these. And whether it's a driving shoulder or trailing shoulder is decided by the direction of twist of the rifling. If it's a right twist rifling, like this picture is showing an example of, from the base here, you can see that the angle of the stria is tilted towards the right. That indicates a right twist bullet. And so the right shoulder on a right twist bullet is your driving edge. This is the one that's going to have the cleanest, most defined cut to it. On the trailing edge, if that rifling is old or the gun's kind of worn, that trailing edge could be a little less defined, and ultimately beside it, you could end up with some slippage where the rifling didn't grip as strongly on that trailing side. But the driving edge is going to be the strong side that you want to be most cautious of, and that's the angle of that driving shoulder should be the dominant angle of your striations on the surface of the bullet. Another thing to be aware of is that you could be seeing seating marks, especially in the GEAs. If your Gs have seating marks, you need to be aware that you don't really care about these. These didn't come from the barrel, which is what the most important markings for us came from the barrel. These ones rather came from when the bullet was seated into the mouth of the cartridge case at the factory. As it was slid into that mouth, whatever imperfections were around that inner circumference of the mouth were scratching across the side of the bullet. And that is not matching anything to the gun. That could be matched back to the mouth of the cartridge case, but that's not what we're interested in. We're interested in seeing what gun fired this, and that information is really at the base of the LEAs. There's also a type of rifling out there called polygonal, and when you're making a polygonally rifled barrel, you start off with the same two steps. You drill through it, you ream it to a precise diameter dimension, straight, and then all of those reaming marks ultimately get polished out. And you get the extra step here of polishing out that barrel, which is actually kind of getting rid of what makes some of the most interesting marks in those LEAs. So that's polished out smooth. And another difference is that at this stage, the actual bore diameter is larger than the diameter of the bullet it's ultimately going to fire. The next step is to take a mandrel, which is a pre-molded or a molded hard piece of metal that is got the rifling pattern already molded into it. And that mandrel is inserted inside the barrel and ultimately hammer forged down, crushed essentially around the shape of that mandrel. Not necessarily with a hammer literally, but it is crushed around that surface. And then the whole reason why the inside of the bore had been polished was because if all of that rough texture was still in there, after that hammer forging took place, that roughness would grip onto the mandrel. You'd never get it out. The fact that it's smooth means that you can slide that out. And once it is slid out, you end up with a polygonally rifled barrel. And that mandrel goes on to make the next barrel in the manufacturing sequence. The big difference here, though, is that there are no shoulders here. You will have, here's your single LEA for a polygonal rifled barrel. Everything, all the markings on polygonally rifled barrel or bullets are quite a bit smoother. They're not as deep, they're not as defined. That makes them quite a bit more difficult, both on IBIS as well as on the comparison microscope. For the experts, these things are even a difficult thing to work with. Your striations will be there. They're going to be a lot less deep. They're going to be quite faint. You do not have shoulders to work with. You don't have defined transition between the lands and the grooves. Instead, it's really almost like a little sort of rolling hill transition between one and the other. And that they're tougher to work with, but there is something that can be done some of the times. You just got to put them in and hope for the best, really. You could come across seating lines here again, and those are from the cartridge case. They're not from the rifling, so seating lines should be ignored when you do come across them. Class characteristics for the bullets, they're called general rifling characteristics, and the GRCs can be broken down by the caliber itself. And the caliber you're going to measure here. With cartridge cases, it's easy. You get kind of a cheat sheet because you can look on the head of the cartridge, and more often than not, you're going to actually see the caliber stamped right there. With bullets, when you recover a bullet and you're working one, you don't always have that information available. If you've got just a bullet brought to the lab or brought to your police department from the morgue or what have you, you don't necessarily know what caliber fired it. You've got to work off of the actual dimension of the bullet itself. So you can work imperial, you can work metric, inches or millimeters, but you want to try to figure out what that bore diameter was by the bullet diameter. Number of Lees and Gs, direction of twist are also part of it. So if we look at the barrel and what that does to the bullet, you've got 4 here with a right hand twist, 5 with a right hand twist, 6 with a right hand twist, and you could even come across left hand twist there. In this case, 6 left is just happening the opposite direction. And we can see that on the bullets that were fired through there. The more that you have, the more Lees that you have, or lands in the barrel that give you Lees, land engraved areas, the more there are, the more narrow they're going to end up being. So when there's fewer, they're going to be a bit wider. So you got the big wide ones with the 4 right, they get a little narrower with the 5, narrower again with the 6, with the right hand twist, left hand twist here. So the way to really get a sense of that direction of twist is hold that bullet or get the bullet in front of you, and from the base, just look to see which way that rifling cants towards. It cants towards the left, there you go, left hand twist. Cants towards the right, right hand twist. Lee and G widths would also be part of the general rifling characteristics, but we don't need to worry about that for bullet tracks because once that bullet's put in the machine and the acquisition takes place, the Lee width, the width of that land engraved area, is part of what's calculated automatically during the acquisition itself.
Thanks for watching. Stay tuned to the channel for future content, and I hope to see you soon. Bye-bye.